step 1, do this division. So e to the ln of 1.5 per hour times t is equal to 1 milligram divided by 0.2 milligrams. And let's simplify that right-hand side a little bit. And either use a calculator or I don't. Maybe I'll just show you how to think about it without. In fact, let's use this to remember how to do division. So I see like this decimal point on the bottom. So that means you could like multiply the top and bottom by 10 to get it to be simpler. Let's cancel the milligrams immediately. So that's 10 divided by 2, also known as 5. So e to some stuff is equal to 5. How do you undo the e to some stuff?
Take the natural log of both sides.
Take the natural log of both sides, or if you prefer, we write it in log form. They both have the same result. So you end up with the stuff in the exponents, ln of 1.5 times time is equal to the natural log of 5. Okay, so what next? Let's see, I should probably divide by this because it's multiplied on this side. And then let's multiply by hours. So t is equal to the natural log of 5 divided by the natural log of 1.5. And kind of as we knew, the final unit should be hours. Nice. How do people feel? That go okay? If you now want to actually know what this is, well, I guess I can tell you that's the same as the log base 1.5 of 5, but that's not actually helpful. Instead, probably you're just going to use a computing machine to do this. And I have the computer pulled up, but I mean, you guys already have your calculators there. What is that number?
Like 3.9.
Somewhere around 3.9. And maybe we'll do a quick sanity check. So let's see, in 1 hour, the population went from 0.2 to 0.3. And so this says if we now wait from there another 3 hours-ish, we should get all the way up to 1 milligram. Yeah, that seems about reasonable. But it's going to go definitely faster than linear, so the time should be compressed. So let's ask just one additional question. So let's suppose we wait 1 full day and ask, what is the population in this Petri dish going to be? What do you need to do to accomplish that? Do we have a model that tells us how big the population is at any given time? And at what time do we want to use this model? At time equal to 1 day or 24 hours. So all you have to do is plug in 24. And what do you get? Well, you'll get whatever it is that you'll get. You'll get 0.2 milligrams times e to the ln of 1.5 per hour times 24 hours. And before you do anything, right, the things in the exponent cancel, which they have to, right? I don't know what e to an hour means. I can't have any units up there at the end of the day. And so I mean, on the one hand, you can just like crunch that out. What do you get? brackets, you wind up with 0.2 times e raised to the ln of 1.5 times 24. You wind up with something around 3,300 milligrams
but should we simplify that at all? That's the same as
43 grams.
And of course, now we're definitely reaching the point where that's an unreasonable number. And one thing that you kind of see here is as the population is growing in this petri dish, there's no way it can continue to grow exponentially fast forevermore. Eventually, it's going to eat all the food in the petri dish. And so really, there will be some constrained growth later on. How many people here have interests lying in the biological field? Okay, cool. Most of you. That's maybe enough that it's worth writing up something about what you should do if you want to study actual population growth models. Because exponential growth clearly doesn't model populations for long periods of time. Like this population of bacteria, if it goes on fast enough, will come on the off, and since that doesn't happen when you open a petri dish, this model fails at some point. Nice. So, let's give one other formulation of exponential growth. So the formulation on the previous page is all in terms of the natural exponential e to the x, e to the t. But let's even just look at the answer, the formula we got at the end. Let's look at this formula. I could rewrite that ever so slightly as this initial population times, and then I could use properties of logarithms and exponents to rewrite this. So let's see. I see a product of two things in an exponential, so I could realize this is an exponential of an exponential. That's e to the ln of 1.5, and then raised to the t in hours. But what is e to the ln of 1.5? You don't need a calculator. What's e to the ln of thing? 1.5. And hopefully that agrees with those of you who started clicking away on the calculators. So you could rewrite this as 0.2 times 1.5 raised to the t divided by hours. Cool. We could rewrite any exponential that way. So here's another model for exponential growth. If you have a population that's growing exponentially, you could write that population as an initial population times some base to the t, where that base is some constant. I guess it better be positive, and it's probably not 1 or your population isn't growing. Of course, I guess constants are still exponential, so maybe you will walk out that way. But if you have a constant population, you shouldn't use exponential methods. So to see that these are the same, well, you can rewrite everything. So just like we did on the previous page, the initial population times e to the lambda t, the formula from the previous page, is the same as the initial population times e to this constant. Oh, I guess it was k on the previous page. E to the k raised to the t. But notice, there's a constant. If that's the constant base b, I get p0
b to the t.
So this is just trying to tell you that, in fact, these two languages are the same, and there's the way to translate between them.
And sometimes, I don't know, it's nicer to treat this base like the unknown, and we'll just see it in action.
All right, so how about this? You have a population of rabbits that's growing exponentially fast. You check it on day 0, and you see that you have 30 rabbits. After 4 days, you have 8 rabbits. I guess these rabbits are exhibiting very fast reproductive cycles, faster than is reasonable for rabbits. But that's okay. This is a math class, not a biology class. How many rabbits do you expect to see at day 10? And the answer is probably going to be quite a few. In 3 days, the population more than doubled.
Let's try to figure it out.
So the initial population is 3 rabbits. So what's P0?
3. And maybe I'll suppress the unit of rabbits. I'll put it in there for now, but I'll drop it as soon as the next step will.
The next thing we need to do is we need to figure out what the unknown base is in this model.
And let's see. So I know that at 3 days you have 8 rabbits, so 8 must be the initial population times the unknown base raised to the t, which is at t equals 4. So 8 is equal to 3 times b to the power of 4. Is that something we could solve for b?
Yeah, right. Of course you can. You could just
Do it. Divide by 3. And then what undoes raising something to the power of 4?
Taking 4 through it.
Taking the 4 through it. So, what do we wind up with? We see that the population at any given time is exactly the initial population, 3, times 8 thods to the 1/4 power raised to the tth power.
And maybe you went and computed what 8 thods to the power 1/4 is, but I think I won't because you really shouldn't do any of those simplifications until the final step. You'll lose information too soon.
Maybe I'll simplify it a little bit. 3 times 8 thods to the t over 4.
Maybe that's a helpful way to think. How do people feel so far? People feel pretty okay? Any questions at this step? Okay, but what was this actually having us answer? What do I care about in this question, really?
How many rabbits there are at day 10?
How many rabbits there are at day 10? So what do I need to do?
Plug in 10 for t.
Plug in t equals 10.
And I suppressed all the units this time. But all the units are in fact consistent, so there's no issue. So the population at day 10 is 3 times 8 thods to the 10 over 4. And let's simplify it as much as we can. 8 thods raised to the power 10 thods is like 2.5, I guess.
Well, 5 halves is equal 4. And to do any better than that, I think we probably just need to use a machine. Oh, maybe I'll see this. How many people want that 3 to cancel with the 3 that you divide by? Okay, good. No one does, because this 3 is inside of an exponent, so there are really 2.5 3's written down in a row.
And well, I could now ask the machine, but presumably you guys have clicked away a little bit.
What is that about?
Ish.
35. Give me the next decimal point.
Well, it's 34.83. Or 8. Yeah, 84 actually.
Which on its face isn't a reasonable answer. So this is telling you there's somewhere between 44 and 45 rabbits, but populations tend to take integer values. I don't know what 8/10 of a rabbit means. So another thing you should keep in mind whenever you're using these exponential methods for population growth is populations take integer values. So these exponential methods, any model really for population growth, will be approximate. They will be somewhere around 45 rabbits. Cool. Any questions before we move on to the next thing that I want to talk about today? Let's talk about interest-bearing accounts. And on the way, we will see the natural exponential e showing up. So let's talk about interest rates, and let's build it up kind of from scratch. Let's suppose you put $5 in the bank account. It has an annual interest rate of 10%. So that means that like after 1 year, you'll see an additional 10% of 5 in your account. So that means you'll have the original $5, then you'll have 10% of $5. 10% is 0.1, so you can do some factoring and see, well, that should be the same thing as you've got $5 times 1 plus 10%. 10% is the same thing as 10 over 100, that's what percent literally means. So you should have 5 times $1.1, also known as $5.50. After 1 year. So let's suppose that I leave that money in the bank for another year. Let's see how much money we have then. So that should be the same thing as starting with that 5, multiplying by 1.1 once to get to the total after the first year, and then I multiply by 1.1 again to get the interest after the second year. That's the same as multiplying by 1.1 squared, right? So you should have $5 times, I'll put parentheses just for emphasis, 1.1 raised to the power of 2. And I mean, 1.1 squared is such that maybe you can remember that that's probably like 1.21, but maybe not. A lot of the computations today, I do want to just do this way. 5 times 1.1 squared. There it is, $6 and a nickel. So how can you figure out how much there should be in the bank if you wait 10 years? What formula should give this? How many times do you need to multiply by 1.1?
10 times.
10 times. What do you get when you multiply 1.1 by itself 10 times? What's the code word for that? 1.1 to the 10th? So that final value will be $5 times 1.1 to the power 10. And I'm putting parentheses there, but the order of operations will do 1.1 to the power 10 before it multiplies by 5 anyway. How much do you have at your 10?
$12.97.
$12.97, and maybe it's really approximate. I guess it depends on how your particular bank is going to learn the pennies. How does that feel? Does that seem reasonable? And I mean, that's not a very big number, but neither was $5. I guess it does say that in those 10 years, you've more than doubled your initial pot of money. All right, so let's think about another type of financial package that one can get. So you can get, there are 2 different parameters that a bank will tell you that their savings account has. There's how often do they compound interest, and what is the interest rate. So let's suppose you take this $5, we put it in an account with annual interest rate 10%, but it's compounded quarterly, meaning 4 times per year. So the way you should read that is that means that every quarter of a year, there should be an effective interest rate of 10% divided by 4 because it happens 4 times. And so let's just see what that means. So that means that every 3 months, every quarter, you should multiply the rate by 1 plus 10% over 4, also known as 1 plus 2.5%, also known as 1 plus 0.25, or just 1.025. So after that 1 year, you should multiply by 1.025 4 times. So if you want the total value, after 1 year, it will be $5 times 1.025. But you need to multiply by 4 times, so you need to raise it to the power of 4. Suddenly that becomes outside of the realm of what's convenient to do by hand. Times 1.025 raised to the 4th power. Got about $5.52. So here's the payoff. Here's a takeaway from this. If you have 2 different accounts that have the same advertised interest rate, but one of them compounds more frequently, it's marginally better. Right? 552 isn't much better than 550, but it is better. In 2 years, you'll need to multiply by that 8 times, so the total will be 5 times 1.025 raised to the power 8. Which, I mean, I could do this, but you guys presumably are also just filling in these blanks in the head. What is that? $6.09, which again is marginally better than it was compounding annually. After 10 years, and you'll have 5 times 1.025 raised to the power of 4 times 10 years. Which is presumably a little bit bigger than $12 this time. What is it actually?
13.43.
13.43. Nice. How do people feel about that? Does it seem okay? All right. So all the point of this is, if you have some interest rate, so some account that bears interest, figure out how many times you need to compound that interest rate and what the interest rate is per period. Multiply by 1 plus the interest rate that many times. That tells you how much money you'll have in the account at the end. So here's how I'm going to start walking towards E. Let's write down that general formula. If you start with some initial investment, or principal, with an annual interest rate of R compounded n times per year, then the quantity and the amount after t years, well, it should be, well, there's the interest rate R divided by n. So that's what the interest rate per period is, because you're dividing the year up into n equally sized chunks. So there are n periods. Each period has a rate of R divided by n. And you're going to compound interest n times per year. So if you wait t years, you need to raise it to the power n times t. So there's some formula. Let's see what happens. So you put $5 into account with annual interest rate 10%, just like above, compounded monthly, so 12 times per year. How much money is in there after 10 years? Maybe before even doing the computation. So let's see. Initially, it was $5.50 if you compound it once per year. It was $5.52 if you compound 4 times per year. Any just guesses for what it should be? If you've already done the computation, you can't take a guess. I don't know. It should be like better than $5.50, right? You're compounding even more frequently, but it shouldn't like be much, I guess. I don't know, let's say $5.54. Maybe there's a guess.
let's actually see what happens. How much money is in the account? Oh, after 10 years. Okay, so it should be bigger than 13. After 10 years. So let's just write that down. It should be 1 plus, the annual interest rate is 10%. So 1 plus 0.1 divided by 12 times per year raised to the 10 times 12.
Right, so that's just using the formula above.
Parentheses are important when playing this sort of game. 1 plus 0.1 divided by 12 times. Raise that to the 10 times 12, because you're going to compound that interest 10 times 12 times. Oh, I forgot to multiply by 5. Nice. So the final payoff is somewhere around $14.53. Which again is a little bit better than it was compounding quarterly. All right, so let's keep playing this game. What if it compounds daily? Your bank wants to be very convenient, so it wants to say, okay, so no matter when you bring your money out of the account, you'll get all the payoff. So we'll compound it every day for you. As long as you hold it in there for a full day, you'll get some interest. Let's see what happens. So this should be 5 times the initial amount times 1 plus the interest rate, 0.1, divided by 365, times 365 days per year, times 10 years. So, I mean, I guess I am off by leap years, but I'm okay with that. And that'll be whatever it is. If you compounded it that well. What is that?
13.59.
14.59? Seems you got?
Well, is there supposed to be a p in front of the equation because you're adding a 5 in front of it? Like a.
Oh, I left it out of the original formula. Yeah. There should definitely be a p there. The more money you put into an account, the more money you have at the end. If you don't put any money into a savings account, you will end the account with no money. Yes, that's thank you for pointing that out. That's important. Okay, cool. So with the 5 there, how much do you have at the end of those 10 years in this account?
13.59.
1359. What if you compounded 10,000 times per year?
13.59.
But a slightly bigger 13.59, right?
Yeah, sure. It's leaning on the right.
So maybe here are some things you notice. As you compound this, as you compound more frequently, even with the same annual interest rate, the payoff goes up, but it stabilizes. The difference from 365 to 10,000 was basically nothing. The difference from 12 to 365 was not nothing.
So what that should tell you is, even when you compound more and more frequently, that should stabilize. And in fact, here's what it stabilizes to. If you have an initial principal P in a continuously compounding interest-bearing account, so it doesn't compound every day, every second, it compounds every moment. The formula for how much interest you'll have at the end will be the initial principal times E raised to the rate R times N, where N is the number of years. And let's just check that this is actually reasonable. We did this computation and saw what the amount you get after 10 years with an interest rate of 10,000 times per year, which is pretty close to infinity times per year, right? 10,000 is pretty big. Let's see what it actually is, though. So it should be 5 times E to the interest rate, 10%, also known as 0.1, times the number of years, 10.
So I guess you simplify that out. What's 0.1 times 10? 1. A tenth of 10 is 1. So it'll be 5 times e. And what is 5 times Euler's number e?
13.59.
Cool. So it does. This formula does seem to work out correctly. So this is actually where Euler's number comes from. If you start thinking about interest-bearing accounts, and you take the period that the bank takes between compoundings, you'll see Euler's number is the base that just has to show up.
And maybe just one last thing. So I think I want you guys to do this computation. So let's suppose you put, again, $5. $5 is all the money I have. Into an annual, an account which has annual interest rate equal to 5%, also known as 0.5. So there's R. Which is compounded either annually, 5 times per year, 24 times per year, 365 times per year, some typos are caught, or compounds continuously. Tell me how much you have at the end of let's say 20 years.
And I mean, I can talk, or you guys could do the walk. How many people want me to talk to one of them before I make you two? Okay. I'll do one. I don't know, 24 times per year. Why not?
So this is going to use the formula. All of these are going to use the formula that the amount, after some number of years, will be the initial investment, the principal, times 1 plus the effective rate divided by n, raised to the power n times t. And if we do it 24 times per year, and we wait 20 years, well, let's see, let's write down all of the things. So the principal is $5 in all of these. The number of times compounded is 365. The interest rate is 0.05. And the time is going to be 20 years. So using those formulas, we see that this should be $5 times 1 plus 0.05 divided by 365 raised to the 365 times 20.
Everybody happy?
And again, if you actually want to know what this number is, 5 times 1 plus 0.05 divided by 365, raise that to the 365 times 20. Somewhere around 1459.
And so now, what do you guys think? Can you repeat that process for these other examples? I think I want you guys to. And there are like a few minutes left of class, so I think that I want you guys to do it. Talk with those around you. And if you haven't done right yet, you can like show me on your way out.
Thank you.
So, that wasn't enough time to make this next sequence anyway, but maybe I'll see how you guys feel. Even if you didn't have time to finish the computations, how many people feel pretty okay about using these formulas? Okay, how many people feel badly about these formulas right now? Okay, if your hand should have gone up and didn't, then we should talk sometime. I think I have an office hour right after this class.
Do you want to see these?
I would have if there was more time. Did it not write down any formulas?
I mean, I was doing it all. Like a formula.
There's an extra. I don't know if you have to use.
Thank you. I mean, I'm just going to put it in the recycling box. Thank you, Jason.